Welcome to qnawire.
Okay, so we have another two-dimensional vector decomposition problem. So let's start off by drawing some coordinate axes because we're told exactly how we want to orient things in this problem. So we'll have our horizontal axis be x increasing to the right in the positive direction, the vertical axis be the y-axis. And then I'll remind you that we number the quadrants starting in the positive direction of both. So that would be the top right-hand corner, and then go counterclockwise in numbering the quadrants. So 2 would be over here, 3 would be all the way down here, and then 4 will be in this bottom right-hand corner. So right off the bat, they tell us, well, we're going to do color in here, that the vector F1 will be 9 newtons in the direction 60 degrees above the x-axis in the second quadrant. So it's going to look a little something like this. So this is going to be our F1 vector in blue. And then we will call this angle over here, nice, theta 1. It's going to be 60 degrees. And then for our second vector, in order to make this drawing as realistic as possible, I'm going to draw it to be shorter than F1 because we know it's only 6 newtons instead of 9. So, and at 53 degrees, it's going to look a little something like this. And we know that we're 53.1 degrees below the x-axis, so this is going to be theta 2. And then our F2 vector pointing in this direction. So this is a schematic of what our diagram looks like so far. Next, we're going to use the head to tail method of looking at vectors in order to decompose this. So let me go ahead and redraw F1 to the best of my ability, and then putting it head to tail, put the second vector pointing down in that direction. So as a reminder, we have F1 over here, and then F2 over here. So now we can draw the resultant vector in yet a new color, and we'll call that R. And so that's going to look a little something like this. And then just for completeness, we'll draw some nice dashed horizontal lines for reference so that we can draw our angles in so that we know what to measure our angles with respect to. So theta 1 is going to be down here, and then theta 2 is going to be up here. Remember that that's theta 2. Okay, awesome. So the reason why we're doing this is so that we can also draw some vertical lines in here, down like this, so that we can see 2 right triangles. So there's one right triangle over there and another right triangle right here, and this is going to tell us how to decompose our F1 and our F2 vectors. So maybe starting over here, let's decompose the F1 vector first into its components, and then this is going to be part A. All right, so starting off with the y component of F1, that is going to be equal to the entire magnitude of F1 multiplied by the sine trigonometric function, specifically of the angle theta 1. And the reason for that is, remember that sine is defined as opposite over hypotenuse, so we are getting that ratio in. And then via process of elimination, or remembering that cosine is adjacent over hypotenuse, f1x, the x component of f1, is going to be equal to f1 itself multiplied by that cosine trigonometric function of theta of 1. So let's go ahead and put some curly braces around these to remember that those two equations go together. Oh, and then one thing I forgot to mention is that cosine is, the x component is pointing to the left, so in the negative direction. So this is actually going to have a minus sign in front of it, negative f1 cosine of theta of 1. Moving right along, let's decompose that f2 vector. So starting off again with the y component, because of the similarity of these triangles. F2, the y component, is also going to use the sine trigonometric function, and it gets a minus sign because it's pointing downward. That y component is pointing downward. We can deduce that from our very carefully drawn diagram. And this is also sine, but it's of the angle theta 2. And again, via process of elimination, or looking at, remembering that sine is the opposite side divided by the hypotenuse, we get that this is going to be f2 of, this is cosine, Let's go ahead and erase that out. And this is cosine of theta 2, because cosine is adjacent over hypotenuse, and then both of these components are negative. We can kind of see that from our initial picture where we knew that f2 is pointing into the third quadrant, so it's going to have negative components for both x and y. So let's go ahead and put those in curly brackets because those two go together. So great, we decomposed f1 and f2 into its constituent parts, but what we're really interested in is the x and y components of the resultant force, so we'll get to that right now. So let's do this in pairs as well to organize our work. The x component of our x is simply going to be equal to whatever that magnitude of the x component of f1 is, added to the x component of f2. We're going to get a very parallel looking equation for the resultant on that y component. Same idea. f1 of y added to f2 of y. Great. So moving right along, we can get a fourth curly bracket pair in there by simply substituting what we found in the first two sets. So copy over f1x. Don't forget the minus sign. It's mostly minus signs here as well. So this is going to give us that cosine component, theta 1, and squeeze in a minus f2 cosine theta 2. So the cosines are going to go together, and then the sines are going to go together. And then 2's always stay with 2's, and then 1's always stay with 1's. So again, we're just substituting our previous relations into the above line, and then let's put a plus sign here just to remember that this is the only positive term. This is going to be f1 sine theta 1, subtracting off f2 sine of theta 2. Okay, and then our last step is to plug numbers in now that we have the analytical form for these two equations. So starting off with Rx, it's terrible looking. We get a minus 9 cosine of 60 degrees, and subtract off a nice 6 in front of cosine of 53.1 degrees. And then that y component over there with a nice positive 9 multiplied by the sine of 60 degrees. Subtract off 6 times the sine of 53.1 degrees. Okay, so go ahead and plug those into a calculator, and then you'll get the following results. Make sure your calculator is on degrees mode and not radians. You'll get a negative, it's 3 significant figures, 8.10, and don't forget your units where we have forces, so we'll get units of newtons in the end. And then in the y direction, we'll put a plus sign here for super emphasis that this is a positive quantity. 3.00, remarkably, to 3 significant figures. And we can go ahead and put a big box around those two answers. Excellent. All right, so this is a classic example of a problem where the second part will be much, much easier to do than the first part because we've set up so much of the infrastructure already. So basically just going to use the Pythagorean theorem in order to find the total magnitude of the resultant force. And that is r squared will be equal to rx squared plus ry squared. So let's go ahead and take the square root of both sides so that we can isolate r and then plug in our numbers from the previous part, which I'll remind you were negative 8.10 squared plus 3.00 squared. Nice little tail on that square roots. And then again, don't forget that we're working in units of newtons, and at the end of the day, you'll get a magnitude of the resultant force being 8.64 newtons to three significant figures. Go ahead and put a big box around that. Awesome, and we are all done.